Today's lesson, we're going to learn about the combined gas law. The combined gas law literally combines the three gas laws that you previously learned about, involving pressure, volume, and temperature. And it's fairly easy to use if you were able to understand the three previous gas laws. Before we learn about that gas law, let's just remind ourselves of what STP is. STP means standard temperature and pressure. Standard temperature and pressure, those conditions we said, were at 0 degrees Celsius and 101.3 kilopascals. That's at sea level. There's also another set of conditions, which is called SATP, which you might run into. SATP means standard ambient temperature and pressure, which means 25 degrees Celsius and 100 kilopascals. That one's more commonly used for room temperature conditions, if you're comparing conditions from one lab setting to another. If a question ever mentions STP or SATP, you can automatically assume to use these temperatures or pressures depending on which one is being mentioned. Now, let's do a quick review of the three gas laws from our last lesson. We had P1V1 is equal to P2V2. We had V1 over T1 is equal to V2 over T2. And we also had P1 over T1 is equal to P2 over T2. So these three gas laws are all combined together mathematically to get the combined gas law. When we look at all three, you'll notice there are similarities. Pressure is always in the numerator. It's in the numerator here, and it's in the numerator here. Same thing with volume. Volume's also in numerator here and here. We never see temperature in the numerator. Temperature is always in the denominator. So when we look at the gas law that combines all three of these together, you'll find that it's keeping all of those placements the same, but you will see all three variables this time. P1 V1 over T1 is equal to P2 V2 over T2. And really, this is the only gas law that you need to know out of all three, because if you know this one, it will give you any of those three above. Here, all variables will change. So pressure will change, volume will change, and temperature will change. But recall from the previous three gas laws, these ones up here, we always had one variable that was constant. So for example, if we took Charles' law, which is this one over here, Charles' law had pressure constant. Pressure constant means we didn't see it at all in the formula. What if we cover up pressure in our formula here? What if we were to eliminate that? If pressure's constant, we eliminate it from our formula, and we get V1 over T1 and V2 over T2. There's Charles' law. So that works out really well if we want to do that. What if we want to make the same assumptions for other ones? What about Boyle's law when temperature is constant? Well, temperature constant means you don't need it at all. Erase it from your combined gas law equation, and look, you get Boyle's law. And then you could do the same thing with pressure and temperature. So if you need to know one gas law and remember them for these four, this is your best bet. So let's just jump right in and try some problems out so you can see what it's all about. So our first problem, a sample of gas is 150 milliliters at minus 13 degrees Celsius and 92.3 kilopascals. What's the new volume of the gas at 103 degrees Celsius and 123 kilopascals? So with these questions, it's really important to write down your variables. The gas starts off at a volume, temperature, and pressure. So those are all our initial conditions. So V1, 150, T1, minus 13, P1 is going to be 92.3. 92.3 kilopascals. Then we're going to look at our changing temperatures, our changing conditions. So new volume is unknown. T2 is 103. And P2 is 123 kPa. So, with this formula, just like the others, there's one thing we have to do to temperature. Temperature can't be in Celsius. Temperature has to be in Kelvin. So that's the first thing you want to check. Temperature here is not in Kelvin. Let's make sure we put it into Kelvin. So if we do our conversions, this will be 260 Kelvin, and this one will be 376 Kelvin. So make sure that you've got those. Then check your other units. Kilopascals and kilopascals, they're both the same here, so we don't need to do any converting. And milliliters for volume, that's fine. Our answer will be in milliliters then. If we want to rearrange our formula, we know it's P1 V1 over T1 is equal to P2 V2 over T2. Now, if you want to use that trick where you're flipping things around, put your unknown, which is going to be V2, on the left, and then have your other variables on the right. And now when I rearrange my formula, I want to get V2 by itself. So T2 is going to move up to the numerator, and P2 is going to move down to the denominator. So my rearranged formula will look like this. V2 is equal to P1 V1 times T2 over T1 times P2. Now I'm ready to plug in my values and solve. So what's going to happen? Just put it all in and do the calculation. All right. So, not hard to put in. Take the time to make sure you've got your formula rearranged properly, and then it's just calculating. 92.3 times 150 times 376 divided by 260 times 123. Here, when we round, we want two significant digits. So in our answer, you should get approximately 160 milliliters. So using the combined gas law, like we said, is very straightforward, just like the other gas laws, but there's a little bit more going on in terms of variables. So just make sure you take the time to identify what variables belong with what conditions, and then you'll be set to solve. Here's one more problem for you to try. So I want you to try this one on your own. So here, try and pause the video and see what you can solve. And when you're ready, we'll jump back in and we'll solve the problem together. Okay, so hopefully you gave this a shot. Let's take a look at the answer. So we start off with a pressure of 48 atmospheres. Our starting temperature was 17 degrees Celsius. We know we'll need that in Kelvin, so we'll put that in right away. And our starting volume is 35 milliliters. We're trying to find the new pressure. The new temperature is 24 degrees Celsius. Again, right away, put it into Kelvin. And our final volume is 4 liters. Now, taking a look, pressure, our answer will be in atmospheres. the question doesn't ask us for a specific unit, so that's fine. We can leave that the way it is. We've got our temperature in Kelvin, but here you'll notice our volumes are not in the same unit. Either make them both milliliters or make them both liters. It doesn't matter, but they both have to be the same unit. So I'm going to change this into liters. So 35 milliliters is 0.035 liters. Okay, now I'm ready to solve for P2. So I'm going to do the same steps that I did with my rearranging, but I'm going to put my P2 and V2 on the left to start to make it a little less rearranging. So if I want P2, that means V2 has to move to the other side. It always goes from numerator to denominator. And the T2 is going to go from denominator to numerator. So my rearranged formula should look like this. Once I've rearranged it, and I've already identified all my unknowns, I can start to plug in and solve for P2. So let's do that. 48 atmospheres times 0.035 liters times 297 Kelvin divided by 290 Kelvin and 4 liters. So when you plug that in your calculator, you should have gotten about 0.4301 atmospheres. And then, like always, don't forget your significant digits. This question needs 2. So your final answer should be 0.43 atmospheres. So it's a short lesson, but hopefully one that's fairly straightforward on the combined gas law. Remember all of the rules that you learned from your previous gas laws and apply them here.